everyone. I'm David Flynn, the CEO of Hammerspace. It's a pleasure to be here and speak with you today. Lay some ground rules. You're welcome to raise your hand and ask questions along the way. I do hope to leave some time at the end to answer questions, but I think it's a lot funner to make it somewhat interactive, and it gives me kind of a clue as to where people are. So don't hesitate to raise your hand, especially if it's, germane to the part we're talking about at the time. I'm here to talk about the Open Flash Platform Initiative, something that Hammerspace is participating in, and hopefully you'll find it interesting. So just to lay the groundwork, and this is something I'm sure you're all familiar with, AI has led to certain challenges around floor space, power, cooling, the fact that it's geographically dispersed. You can only get so many watts of power in any single location. So AI is sort of fracturing the big monolithic cloud to where instead you have quotients of GPUs in different locations. Some people are even taking it to the extreme of putting GPUs at the base of windmills or where you burn off the natural gas off of oil wells where energy is cheap and otherwise wasted. So GPU computing has basically pushed, of all of these, it's the power budget that's the most limited. And you would think, okay, cost of power, that's only so much. But the truth is, if you run out of power, the opportunity cost goes asymptotic. If you can't put in more GPUs, you're stuck, and it's the value of the GPUs that you didn't put in, not the cost of the electricity that matters. So of all of these things, the biggest limit is power and cooling. However, rack space is a good proxy for that. And it's something more visual, because we as humans, you can visualize that. Wattage is harder to visualize. I view those two as being coupled because power density controls the amount of rack space. But in reality, what we're optimizing for is the efficiency of power and cooling. Now, why? Because storage will typically take 10 to maybe 20% of the power budget in the data center. And you have folks like Meta who are actually taking the hard drives out of their website to reclaim the wattage so that they can put in GPUs. So hard drives are dead, you just don't know it yet. And the thing that's killing them is the power budget. But the only way it gets there is if flash actually takes less power than hard drives. And as flash is today architected, that is not necessarily the case. Flash isn't inherently lower power than hard drives because we've been chasing flash for performance, not flash for capacity. So what you're going to hear about today is how flash can become the capacity tier. And if I may just go back and say, with my previous company, where we introduced what became NVMe, Fusion IO introduced the concept of flash being used for enterprise high performance. Flash for the performance tier happened those 15 years ago, but flash for capacity is only starting to happen now, and that's because power budgets are a forcing function thanks to AI. Now, the opportunity is to change architecture, to build a storage system with standards-based plumbing. I'm going to set aside the exotic stuff in the supercomputing world. Nobody has time for that. There's not enough talent to go around for everybody that's doing AI. So it needs to be standards-based and built in. The challenge with traditional architecture is you have two layers of servers. In all of these systems, whether it's Cumulo, Dell with the Isilon EMC product, or NetApp, or VAST, they all have a two-layer architecture, and this is born out of the fact that storage started very simple. A client connects to a storage server to talk about data in the file system. It has to go through that storage server to get to whatever. So it ends up going through a controller node or protocol node. VAST calls them C nodes to D nodes. This is typically more block storage based. This also happens to be where the file system is generally applied. These are C nodes. VAST calls those D nodes, and they're very proud about the all-to-all connectivity here. My view, and they use NVMe over Fabrics, which we also pioneered at Fusion.io, but quickly realized this is the problem, the architecture for scale-out NAS, and it is a problem because of the protocol. On the other hand, if you introduce a true parallel file system protocol, you can take the controller layer and move it to the side, out of the data path, and allow the data path to scale. The metadata servers are much smaller and finite in size. It's not like you need to go through the controllers. This is the difference between proxying and routing. Imagine how bad the internet wouldn't scale if your DNS server had to proxy all of the traffic to the domains that it resolved. That's how broken this architecture is. It's like having to go through your DNS server to get to anything behind it. This is DNS for data on the right. That's a true DNS architecture. You talk to a control plane and you get a routing information. One of the analogies I like to use is these are surface streets where to get to multiple destinations you have to go through an intersection. That's like going to an air traffic control tower and then being able to make direct flights to any of numerous destinations. Yes?
How is that different from direct NVMe? When you say data path direct
NVMe over Fabrics?
The blue sign, you say that it's on the side, right?
So that data path is NFS legacy v3, and the control plane is stalking NFS v4. To get in more detail, the way it works is the NFS 4.2 with flexible files allows the client to mount the metadata server as if it were the file system. That's like going to the card catalog in the library and envisioning that as if it were the library, because pulling a card out of the card catalog actually automatically gets you the book off the bookshelf. So this goes from a simplistic 2-1 relationship, a client connects to a storage server, to a 3-way, but it's not just 3-way, it's N-way. I connect to a control plane and then it routes me anywhere. This is liberating, and it's what actually allows for us to disintermediate the need for that layer of controllers, that big wall of proprietary IP between your clients and the storage media. Now, some of the enhancements, when I left Fusion.io, I went and recruited the Linux kernel author and maintainer of the NFS client stack. That's Tron Mickelbust, our CTO. He often speaks at these. And I said, Tron, can we make this work? Because the industry tried to make parallel NFS work some 15 years ago, but performance was a niche. The existing NAS vendors already had their file systems architected around the old stuff. They would have had to throw it out and start over again. No way NetApp was going to throw out Waffle or Isilon throw out OneFS. So the standards body effort kind of predictably failed. But one of the main reasons it failed, by the way, is back then people were still worried about Solaris and Windows and VMware ESX and the BSDs and AUX. And every single one of those has a different file system layer. The file system is at the heart of the OS. It's one of the most, if not the most complicated part of the operating system. And they all have different licensing schemes. So the industry was going to have to write this much more sophisticated client that knows how to do the look-aside. We're going to have to write it for every single one of those OSs. It was never going to happen. But when I left Fusion.io, I had a thesis. At some point, high-performance file becomes a mainstream thing, and AI has made that happen. And when it does, high-performance file is going to need to be standards-based, native, and built in. It's got to be NFS. Just like Ethernet, there's Ethernet and there's Ethernet. There's NAS and there's not NAS. It has to be NAS so that everybody can do it. But the thing that we had was I figured that Linux would consolidate the OS landscape, at least when it came to performance and scale, because it already had, 15 years ago, Linux had already consolidated the HPC world, and anybody doing performance, any supercomputer on the planet, no matter how exotic the architecture, was based on Linux, because you couldn't afford not to. Well, and that is the case now with AI. So what I suggested was, we can make this very sophisticated client work if we only have to do it for one OS. And we can do that by getting the kernel maintainers. And I now have a whole staff of NFS kernel maintainers, and we're making very extensive changes. One of those that's very powerful, that is only going upstream now, is the ability to move data from NVMe out the network zero copy with a file system applied. The CPU doesn't have to touch the data. The difference that this makes is profound. It means that that data path, that NFS server there, can just run standard Linux with the kernel NFS server, and on a typical node, if you were to run with x86, 64 cores, 128 cores, it will saturate those cores just to try to fill a 400 gig network, and it'll still struggle. With the NFSD direct extensions, it can fill that with 15% CPU utilization, meaning next to no CPU. What I'm saying is we can serve NFS and file system semantics at the efficiency of NVMe over fabrics. And not only at the higher semantic level, but it can be done out TCP/IP and an IP network. It doesn't need RDMA. We can do zero copy over TCP/IP without even RDMA. That's very powerful. It closes the gap with RDMA networks. So the storage node would use NVMe. The CPU is directing traffic, just kind of like it does NVMe over fabric. And then it's moving the data to the NIC without the CPU ever touching it. This is NFS, TCP/IP, served with NFS Direct. It's enhancements to the kernel NFS server in Linux that allow it to move data without having to copy it through the buffer cache. And it's profound what that means in terms of throughput and performance. It basically means you can get the performance of NVMe over fabrics, but with standard Ethernet and with a file system. Yes?
So could you do the same thing with DPU?
You're jumping ahead. That's exactly what OFP is. Thank you. We'll get there. Wait, just a couple of points here. Closed systems, the data services are in-band. Snapshots, clones, all those things have to be done in-band. The data is written to the underlying storage through the controller in a proprietary format. The system can orchestrate data, but only within itself. In an open platform, anything is your storage. We can use NetApp, Isilon, VAST, or just standard Linux with the kernel NFS server. Anything that speaks NFS v3 is a storage node in a greater parallel unified namespace. So at the end of the day, has profound implications here. It no longer locks your data into specific storage silos. It allows you to use commodity flash, standard Linux, no special IP needed to be a storage server. It's the entire data path, from serving the data to consuming the data, that's all just standard Linux plumbing. The control plane, the air traffic control tower, that's what's hammer space. So with OFP, a DPU or IPU running standard Linux, it's embedded within the storage. So you jumped ahead a slide to that. What does it look like in practice? Well, it's nothing but NIC, nothing but net. Go straight to the network. Now, you can say, we tried this before with NVMe over fabrics, and I'll tell you, that was a stupid idea. Where's the file system? Somebody has to put a file system on that, which means a whole layer of servers to add a file system, or it's a local file system, which means it's not shared data. So there is no good solution if you're serving block storage. It made no use to put NVMe directly on the network because somebody's going to have to put a file system on it. And it's either a layer in between or it's the client. And if it's at the client, it's a local file system. It's not shared data. So this, however, allows the file system to be applied in the NIC because it's nothing but Linux and it can serve at 0 copy at an NFS level and even out TCP IP. Questions?
So is this an NVMe SSD Ethernet or is this still PCI and NVMe?
So these are standard U.2 to a DPU. So it's going over NVMe, PCI Express, and then that's being served out the network. Now, a future incarnation of this might be putting Ethernet directly on the SSD controller and disintermediating even PCI Express. Why would you do that? It takes a lot of power to drive signals over copper. And if I can just go from flash to a controller and then out Ethernet, I've bypassed not only 2 layers of servers, but I've also bypassed PCI Express entirely. Now you'll remember, maybe, the whole thesis behind Fusion I/O and what led to NVMe was disintermediating the storage controller, the RAID controller, the buses like SATA and SAS, and those protocols, and storage networks like fiber channels, said screw all that. That was made for hard drives. It's too slow anyway. Let's go upstream where you would have put the fiber channel card, where you would have put the RAID controller. This is saying, let's step over the server itself. But the only way we're going to step over the very server and go directly to the network is if you can apply the file system with such light weight. And that's what these extensions to Linux with NFS Direct, NFSD Direct. NFS Direct is the client side, allowing the client to be configured to go 0 copy, even without the application knowing or caring. NFSD Direct is allowing the server to go 0 copy. Okay, now this is great, but it's using U.2 devices. And you'll see another innovation here, and that is proposing to get rid of hot swap. Why does hot swap exist, and why would we want to get rid of it? Hot swap is because hard drives fail, and they were cheap compared to the system they were plugged into. Here, the SSDs are only occupying a fraction of a NIC. That's the opportunity cost to not swapping them out and replacing them. The argument we're making is that when you get to such high density, power density, space density, and efficiency in the infrastructure, there is no measurable opportunity cost that would make you want to fix it. Just let it sit there failed. It's not like it's occupying anything valuable. You'd spend more of your money sending monkeys out to replace them than just allow it to fail in place or degrade in place. So it is my contention that hot swap is another holdover from the hard drive era that we can't get rid of soon enough. The capacitance that are required, the rigidity that's required, where the connector goes, all of those things are because we're trying to maintain hot swap. If you abandon hot swap, you build something that looks a little more like a memory module. The connector is along the long edge. The controller is in the middle where you get the decent signal integrity. There's no capacitance because it's not going to be unplugged. The capacitance moves to the entire sled along with the NIC, which gives you the value of power holdup so I can acknowledge writes as soon as they're received over the network, which allows it to be even faster with writes. I saw some questions or commentary in the back.
Yeah, the DPU is 800 gigs, so you're kind of aligning the position with the 800 gig DPUs whenever they come out, and then you have enough processing power on the DPU in terms of units to run your stuff.
So I will tell you that we're using, got to go quicker? Oh, sorry. The question is the DPU matching 800 gigabit and what kind of horsepower? Well, Bluefield 3 is a bit behind the time. The Intel IPU is getting refreshed. It's going to be better. But the one that we've chosen to go with is actually Excite. And this thing has 64 cores of 2 gigahertz Neoverse N2. With the floating point, not that we need floating point for serving storage, but you could embed some processing with it. The floating point, vector floating point, means that the one chip has actually 2 teraflops of horsepower. So we're using a DPU that has a little bit excessive horsepower. Doesn't really need it. It's allowed us to show full saturation of an 800 gigabit link. Yeah. So yeah, unfortunately I don't have a diagram here of the DPU board, but it is more of a server on a chip. Because what's really happening here is RISC and ARM specifically in the data center displacing x86. And if you're going to displace x86 with RISC, you're also going to want to tighter integrate it and have it be a server on a chip. We don't want to architect servers the same old stupid way with a bunch of adapter cards and other crap. It's going to be a server on a chip with the NIC. Some of these guys, like the Intel new Mount Morgan, actually puts the memory in the same package. So it's a server in a single chip with memory and everything. It makes it a little bit more fixed amount of memory, but it actually has huge bandwidth then because it's all on chip. Yes?
I understand where you're going, but however, the server may do other functionality like inline data encryption and decryption.
Perfect. Yep. So the question is around accelerators. Yep. Yep. Yeah, you will see, the question was around accelerators like encryption and so forth. By the way, one of the other enhancements that we have that our CTO and the Linux community we've been doing is adding TLS into NFS. So you can secure the network traffic line rate with hardware accelerated TLS. None of this Kerberos crap and slow things like that. You're more likely to get hardware accelerators from a DPU than an off-the-shelf server. The DPU guys are putting in compression and encryption and all of these things in them. Kind of redefining what the server actually is. But good question. So those storage functions are actually embedded in there. Okay, this is what it would look like if you built purpose-built form factor for embedding. I depict it here without the heat spreading. You would still need heat spreaders, so don't get me wrong. Even though you don't need the rigidity for hot swap, you're still going to need some thermal material. One of the other key advantages of this architecture is you could make it water-cooled, high temperature direct contact water-cooled. You can't do that with individual SSDs very economically. They're too small a unit. You could think of this as a JBOF pivoted to where you have an exact kind of amount of flash with the network adapter to make a match. Actually, in something like this, it's the DPU that's more likely to fail. The controllers, the flash, they're going to have die level redundancy, potentially double redundancy from the die or self-healing. It's just like with a JBOF, you're going to have the server is more likely to fail than the SSDs being plugged into it. All of this is designed to OCP standards to be toolless. Basically, you unplug the network adapter, the power is automatically connected on the back when you slide it in. So this is what it looks like in a full tray. It's 24 petabytes using today's 2 terabit die. Now, not many people are going to fill a rack with these, but with 1 or 2 sleds, you might even leave them partially populated. You might just put 1 or 2 sleds in a tray in each rack and leave expansion capability. The density being 10x any other flash system out there gives you the opportunity just to reserve 1 U under your top of rack switch. And you can just add units of 4 petabytes in a sled. Put that in perspective. Vast, pure, all about flash density. But it takes an entire rack of gear to match what you could do in just 2U when you get rid of all of the servers and go to nothing but NIC around the flash. To do this, and by the way, it's a parallel file system, so all of those OFP sleds, each one of them is 800 gigabits worth of performance. It was what? What was the bandwidth? Yeah, 4.8 terabits a second of bandwidth in 1U. You're not going to get 4.8 terabits a second from that entire getup. And what you could do to get a full parallel file system, let's say you're using Lustre and DDN, it would take 2 racks to get to that capacity point. Now, in that case, you might want to go with units that are smaller than 4 petabytes to get more bandwidth. But what if you put an entire rack full of this? It's an exabyte of capacity in one rack. XAI just procured an exabyte, and it took them 20 racks. This is one rack with room for the switch and power and still under 30 kilowatts. It's a game changer. To do an exabyte of tape, robotic tape, takes 30 racks. So the thing to get across here is that exabyte is the new petabyte. People are buying units of exabyte, and petabyte's the new terabyte. It's what you got to be able to deploy in one little thing. Now, the cost implications of this architecture are profound. The servers and internal networking required to build one of these NAS systems, I didn't believe it when I was talking with some of the folks who had worked at VAST and Pure. They were telling me that over half of the bill of materials, over half of the cost, is not the flash. Over half of the cost is all the servings, all the networking, and all that stuff. Forget software. I'm saying over half of the cost of the hardware is stuff outside of the flash. 2 layers of servers, all the chassis, all the networking in between. If we just were generous and said it's only 30%, that we could disintermediate 30% of that cost, that means instead of 1.4 million to do an exabyte, it's 98 million. Your OPEX is directly proportional to the power, space, cooling, servicing, which all drops by 90%. But here's the thing that the team at Meta pointed out that I hadn't been calculating, and that's that if it's built around servers, you're going to get maybe a 6-year service life, more like 5 years. You can't guarantee, you can't keep servers propped up and running by much more than 5 or 6 years. But if it's flash and a NIC, and the flash doesn't even have to have hold-up capacitors, you can have bigger, more reliable capacitors at the sled level, there's no reason this stuff can't last easily 8+ years. And when it comes to capacity, not performance, flash for capacity, it's petabyte years. How many years worth of retention are you buying? And that means the TCO savings are massive. For the same dollar, buying 2 to 3 times as much capacity because you're not spending all the money on the server infrastructure that just limits the lifetime. Those servers force you to end up throwing the baby out with the bathwater. The flash is what really matters. That's where all of the value is, and yet you're having to throw it out because the server infrastructure. When I mentioned this to the team at Los Alamos, they were like, yeah, we've never decommissioned a storage system because the flash is worn out. It's always because the servers can't be maintained. So this is, yeah. So at a system level, yeah, the repeat, if a device fails, what happens? And at a system level, the redundancy is handled at the pNFS level, cross sled, cross device. And you can take temporary outages, so you could unplug the network and pull it out and replace the the DPU or replace an SSD if you want to, but I happen to think with this kind of density and efficiency on the consumables, space, power, cooling, it doesn't really even make sense to want to service it. Now you do have to have things like media level encryption and external keys, because some organizations want to guarantee that that device doesn't have data on it that's a liability, and now that it's not functioning, you can't track it. So you better have the ability to virtually erase it by forgetting the keys. But then you can just leave it failed in place. Yes?
Where is the metadata? Is it a separate server or is one of those?
No, so that's the key of the parallel file system, is the metadata is a separate system, which scales much more optimally because it's just tiny little packets and small amounts of data. So the control plane separate from the data plane, metadata separated from data. That's the whole key, is that what the data is, its metadata, is separated from where the data lives. Yeah, it's a cluster, redundant. And we are toying around with using the same DPUs to actually run the metadata service. But you could use big fat x86 servers for that if you want to. Yep. So, good sponsorship. This doesn't include some of the more recent additions to the initiative. This ultimately will become an OCP spec, but this is, while Meta is pushing for higher density NVMe devices, this is saying get rid of the servers altogether, go to the DPU, and get rid of hot swap, go deep into the rack with something that's optimized for it, have that become the field replaceable, field serviceable unit. Those are a couple of steps beyond what they're currently at right now. But it's my belief that just as Fusion I/O ushered in the era of Flash as the performance tier, this architecture will allow us to usher in an era where Flash is the long-term retention capacity tier. And just in time, because no data is ever cold in an AI world, we have to be able to rehash through it. So even the archival needs to not only be active, but have decent performance. Now, I've presented this as for the performance tier, but the truth of the matter is it has higher, as the capacity tier. But with 800 gigabits on each of those, I could put TLC, lower capacity devices, and get something that has the highest performance density on the planet of network storage. And that's one of the things we're doing with Los Alamos to demonstrate what it would take to be the checkpoint store for their next big supercomputer. They need something that can write 10 terabytes per second, around 100 terabits, and for us, that's half a rack. And with TLC, it doesn't even have to have that much capacity. I think they're talking about 100 petabytes. So you could mix. You could put TLC in some and QLC in others. And the orchestration environment can do the tiering for you. So if you want to front end things with TLC, then later go to QLC, the parallel NFS data orchestrator, that separate control plane, can do that for you and allow the initial writes to be captured on the TLC, and then only as the data is cooled off and gets demoted can be put into QLC. All right.
There was one report out that the flash failure is number one from Meta, right? There's a number of things. Do you have any orchestration tools, given there's so much flash, that you can show graphically that what's happening on the...
Yeah, actually, our platform, that control plane, aside from being the file system metadata, what all the data is, the directory structure, access controls, all of that, the other key function is to manage where the data is placed and to decide when to move it and actually affect the movement of data. So the data orchestration is key, and data orchestration is not just data management with a new fancy marketing name. Data orchestration means that the data movement is happening from behind the curtain of the file system namespace. That movement is happening transparent to the ongoing access, and while the identity of the data stays unified. It's the same data. It's just been shuffled around behind. And so by being an open platform where anything can be your storage, it allows the more traditional management of data to now be an autonomous function in the environment, data orchestration. So the tiering up, tiering down. And one of the things we don't cover in this presentation is that NVMe inside of the compute tier, NVMe inside of your DGX or HGX GPU servers can also be storage in the environment. That's what we call tier 0. And with these same NFS direct enhancements, they can serve peer-to-peer without being subject to noisy neighbor problems because it doesn't take a bunch of CPU to get the data on and off the network from each other. So NFS direct is absolutely a key enabler to having the performance tier migrate forward into the compute tier as tier 0. So our vision for the future is that NVMe is still around, but that's for flash in the compute tier, and flash for the capacity tier, we get rid of the servers altogether and go to nothing but NIC down there with, oh yeah, if you want to hear about tier 0, that's going to be discussed tomorrow. Floyd's going to talk about tier 0, the new performance tier. Yep.
Do you have a software stack of your that diagram, the hardware you build up? How do you have the SDK and all the NFS servers running on GPUs?
So Hammerspace is deployed that metadata server, and I'm not quite telling the whole story. There's also some scale-out microservices that do the data movement and get in and shuffle things around when you need them. See, here's the thing. Those storage devices, they don't need any custom proprietary software. Everything is just Linux, NFS server, it's all Linux. Client, that entire blue path is just Linux top to bottom. Now, if you were to set up, say, a container environment and can run some microservices there, we've got some important microservices you'd put there. The data pumps that are moving data around to rebalance or to resilver or to re-encode. You'd want to put that stuff down there. But those only get involved when you're actually needing to touch the data for other functions. They're not in the data path while the client's accessing it. Yeah. How are we doing on time? 10 minutes. See if we got enough questions or stuff to cover 10 minutes more. So, yes?
So those data service things are running, excuse me, so those data service things are running on the DPU connected?
So in our
instance?
environment, we're going to have plenty of horsepower left to run the data service functions on the DPU nodes. Those get involved only when you go to shuffle data around or re-encode it or the like. Or when you go to translate protocols, like serving S3 or serving SMB, because those aren't parallel protocols. So you have to go through a bridge, and that's one of the other services. Yes, question in back.
How many storage tiers do you envision in this architecture, right? You mentioned
Yep.
PLC, and the second part of the question is, how long term?
So the question was, how many storage tiers
Yes.
would you envision? And the second one is, how long is long term?
Yes. In the summary slide, you had long-term storage,
Mm-hmm.
and that depends always on what's your reference.
Yeah. Yep.
Long-term may mean something else than what they.
Yeah. So the number of tiers, honestly, we have some customers who are doing tier 0, and there's such an excess of capacity that it's also their capacity tier. You can't buy DGX servers without 30 terabytes. Actually, that's already been upped at 60 terabytes. Any new DGX, HGX comes with 60 terabytes of NVMe. Los Alamos deployed 1,000 nodes of DGX, 8,000 GPUs, and that meant they had 30 petabytes. Right? That's a lot of storage capacity. So the new performance tier can easily have an excess of capacity to be the capacity tier 2. Your capacity tier, OFP, is so efficient at getting the data on the network, it could be your performance tier. So you don't necessarily need both. It starts to become a question of how do you want to operate your environment? Do you want it separate domains or the same? But I do see long-term retention will involve orchestrating data to other sites and sticking them in very safe encodings, like putting them in Glacier, putting them in S3, and so forth. But what we see is once you move to a world where data is orchestrated, you can have a plethora of different tiers and physical locations, and you can mix and match them with policy. And in the process, you're getting rid of backup and restore and DR and all of these business continuity workflows. They go away. It's just other orchestrations of the data. Yeah.
Two questions I have quickly. One is that you mentioned, Lawrence, there were more El Capitan there, supercomputers.
So Los Alamos was the one, and that's ATS-5.
Yes, and then they have an architecture Rabbit where they can do the checksum locally on the flash and then they shove it down. So you have something similar
So
to
if you
accelerate
use
checksum?
tier 0, then you don't even notice any difference. It looks
because
like shared
directly
storage.
writing. Okay.
So we're doing that today to show checkpointing in GPU AI workflows. And they open a file and write to it on a shared file system. They don't even see, each node doesn't even see that the file he opens happens to be instantiated on the local tier 0.
I know this is NVIDIA certified storage architecture, right? That GDS works and all that thing works in
Yeah.
there.
And the beautiful thing is because it's NFS. So
Yeah.
NFS Direct just works, or sorry, GPU Direct, all that just works because that's the standard
So
plumbing.
one more question. You mentioned WAST multiple times over here. WAST has an architecture they're proud of, DASE, right? Distributed architecture, shared everything. So global namespace on every one of the clients, they can see it. And then they have the metadata they push on SCM on every D node in there. So they say that they can rebuild the whole architecture much faster and all that.
They still have to have 2 layers of servers
Yeah,
and
yeah,
an
they have
internal
multiple.
network and all of that mess.
Yeah.
It's much more powerful and efficient if the control plane can be separate from the data plane. They call D nodes and C nodes. That's the combination of the two, but the data still has to flow the same way. Now you're just overloading the same physical hardware doing both functions, but you still have to do both functions and the data still has to make all the same network hops. That's why tier 0 is not the same as hyperconverged, because hyperconverged is taking that controller function and putting it on your compute node, which is a really bad idea because now the compute node is having to do a bunch of other stuff. With tier 0, it's really just pure play, 0 copy, moving data to and from NVMe and the network.
Curious, are you bigger than WASP in revenue? I'm just curious.
We can't say. I will say this technology took a lot more to build. And VAST, I'd say, is a little more developed in their go-to-market. VAST has been around longer than we have. But velocity-wise, that's a different question. Yes?
Thank you. So let's say that you did just have a pool and it was all tier 0. Could one of the client servers access the data from the other
Yeah.
one from a tier 0?
Because the way tier 0 works, also, tier 0 requires no custom Hammerspace software. You simply export local NVMe using Linux's built-in NFS server. And it becomes a storage supplier, not just a storage consumer. And so they can serve each other peer-to-peer. With 0 copy and with RDMA if it's on an RDMA network, because you can serve NFS RDMA.
But you're using SPDK there, right? So to get the 0
No.
copy going.
No. SPDK is a user space thing. This is all Linux kernel. The beautiful thing about being in the Linux kernel, you can actually use IRQs.
That's in the kernel, right? So,
No, this is in the kernel.
so 0 copy, you're
0 copy in the kernel. You're not going to get more bare metal than that. Right. SPDK goes through a lot of hoops to do things in user space, one of which is to put whole CPUs in busy burn loops, polling for network traffic because you don't have access to IRQs in user space. It allows you to drive great performance numbers. It looks awesome, but you're sitting there burning CPUs. So go to something like Weka. Weka burns like 6 or 8 CPUs just sitting there spinning to poll. That's what happens when you use user space and libraries like SPDK. You can get really low latency and do all kinds of great stuff, but you just burned a bunch of your horsepower on your compute nodes. Yeah, exactly. Anything user space is going to be major handicapped. The way to put it is this: you're not going to drop a storage software stack on top of Linux and have it outperform what Linux can do natively. Just not going to happen. So fixing NFS to actually do this is the right solution. And that's exactly where these new standards and enhancements into Linux. I'll give you another example. In Tier 0, when the data is on the exact same node, and you're not having to serve a neighbor, when it's on the exact same node, we've enhanced Linux to recognize that it's serving itself and to step out of the data path to where it's direct NVMe access. It doesn't even have to go through the NFS client and server to go through a loopback network or any of that. It actually is a sideband protocol where the NFS client and server goes, hey, are you me? Oh yeah, I'm you. What are we doing talking through this stupid serialized channel? Let's just hand pointers to memory buffers. And boom, you get the full performance of local NVMe. And by the way, Tier 0 is also how we're going to allow GPUs to directly access data on local NVMe, data that's part of a global shared file system that can simply be orchestrated to be resident on the Tier 0 so that with NVMe, the GPU can directly access it. Yeah, that ultimately, NFS will provide a shared namespace, parallel NFS, and the ability to orchestrate the data. That's how you'll get the data into position so that the GPUs can then start accessing it.
Have you tried that with one FS, tried with parallel NFS?
Yeah, they tried that the 15 years ago when there was no demand driver, and they would have had to rewrite their entire file system. So they shelved that a decade ago.
Do you sell the box, the hardware, the flash, or this is just any commodity?
So yes, we are actually bundling and selling it as a full system, because in the AI world, even the hyperscalers can't get enough talent, and they don't want to waste the time doing software defined. So managing the supply chain, dropping it in as a pre-integrated system, even at the exabyte scale, that's how much in a hurry they are. So, I thought, let's build the company as a software defined and allow people to source hardware. OFP, the designs are going to be in the open source. I don't want to actually own the hardware. I just want to take the hardware to the logical conclusion that makes it impossible for these guys to follow.
So with PLC, you will even double it?
With nearline flash, that'll double again. It'll be 2 exabytes in a rack. Yeah. Yes.
I think you mentioned that the error correction is handled in the pNFS layer?
The distributed erasure coding.
Yeah, exactly.
Which does have checksums and does cross-node error recovery.
Right. So in the case where a sled fails or a module fails, does
Correct.
the client perform the reconstruction?
Yes. The metadata server directs those data services. Those are the hands and fingers. So the scale-out microservices get in and move the data, rebuild it, re-encode it. Those services can run anywhere. In our platform, we are going to locate them on the DPU as part of that.
But so do you have to wait for reconstruction to complete in the background before you can read the...
No.
Okay, so there's also a client-based reconstruction path.
So yes, the client is reading and writing through the erasure encoding so that it can continue to function.
Yeah, okay.
But you might need to rebuild something.
Right, and
In
that happens in
case,
the background in parallel.
That
Okay.
happens in the background.
Thank you.
One of the other key enhancements to parallel NFS is that we can pick up and move data and even transfer encodings while it's undergoing I/O. So if you're familiar with storage vMotion in the VMware world, where you can move a VMDK file while your VM is running, we do that with every file. We can pick it up and move it while it's being changed. Yes, another question.
It's a comment mostly. You had mentioned that if it is fail in place, the media encryption key or the derived or the keys that from which the media encryption key is derived need to be remote and should be able to be erased.
Yep.
The comment I have is OCP lock is defining along the
Some
same
of that.
lines.
Yep.
And also from the TCG storage workgroup, we have just publicly released the multi-party media encryption key, multi-party authorization media encryption key
So
spec.
it takes more than one coming together.
Yes,
No
yes.
one can
And
authorize
it's a work in progress release, and soon after we will be releasing as a full spec on that. So.
Oh, that's cool. Yeah. Yeah, I think encrypted drives and external key management are part and parcel to degrade in place because of if the device is dead and you can't inventory it, then how do you know somebody didn't take it? And that's why it's not answering, right? What's that? Nobody has time for science projects. It has to be standards-based. Yeah, DDN, WECA, those guys are falling off the map when it comes to AI. People have to move at too high a velocity. You need it to where every IT administrator on the planet knows how to run it. That means it has to be a standard.
So no SMB then, right?
Well, SMB is standards-based, and we do support SMB and S3, but those are the scale-out microservice layer that can take the old protocol and translate it to parallel NFS. But those two can be co-located down on the DPU. So we serve S3, we serve SMB, we even serve NFS v3, but those are all done through a scale-out microservices layer. It's stateless. It just does a bridging function. It's less than optimal because you have to go through an intermediate. It ends up being like this, going through that intermediary. It's translating NFS v3 to parallel NFS. Yeah. Another question.
Hey, David. Thanks. Great talk as always. Have you been looking at whether it makes sense for GPUs to initiate storage I/O, and if that is true, how you would integrate that into this? Like, how do you see those fitting together, or do they fit together?
So, compute in storage, or push down?
GPUs like BAM, right? So the GPU actually
the GPU
initiated the I/O
request.
Yeah.
So tier 0, I believe, and NFS, parallel NFS, will allow the work that NVIDIA and others are doing to give the GPU direct access to NVMe, will allow us to extend that to a shared namespace that's globally orchestrated. And it also answers how do we get the data onto the right node? Because with an orchestration platform, it can do the repositioning and re-encoding of the data to put the data on the GPU server itself in the first place. It's like an operating system does demand paging to move data from storage into memory. If we extend the namespace out onto the network, we need something that can do the movement of data across those systems, and that's what data orchestration is. It's demand paging extended out into the storage to go across different storage tiers and different positions for the data within a greater cluster.
So maybe just to touch on that, so you see the GPU like basically issuing NVMe commands. You don't see a more file type semantic coming out of the GPU?
I don't think the DPU will need necessarily to have the file semantics, because with XFS and other file systems, you can get the block mapping out, and you can hand it to them. It's just metadata they need anyway. But it might help to get rid of the FTL and make a more directly mapped, use anonymous writes and other things so that the data is laid out on the NVMe device in a little more sane way. There's no reason to have a file system and an FTL and have to have all those translations happening. Wouldn't it be nice if you could hand the GPU the actual physical NAND address and go straight to it?
That's what the NVIDIA does with the GPU direct AI kernel initiated.
Yeah, but it's still going through the FTL on the SSD. Somebody else is still mapping the block to the NAND. Why do that? If you pull the FTL out of the SSD, combine it with the file system, hand that metadata to the GPU, he can be talking physical NAND addresses. Yeah, similar. All right, you guys have been great. This is the last talk today. It's not like somebody else is coming, so I'm happy to continue to answer questions, or here individually. So, thanks.